Another example that appears in slide number 16, we have this amplifier circuit where this is V input. As you see, it's connected towards the source of the amplifier. The output is taken from the drain. So the input towards the source, the output from the drain. So this is a common, what's the third terminal? The common gate. So this is a common gate amplifier. Common gate amplifier. So it says here, take lambda equals 0, which means ignore RO, or take RO as infinity. Find the terminal voltage gain between V output and V source. V output and V source, the voltage of the source. And also we need the overall gain between V output and V input. So we need V output over V source, and we need V output over V input. And also we need the input resistance and the output resistance looking from these points. So we need to calculate the input resistance looking directly at the source. Looking directly at the source. And we need the output resistance looking directly at the drain. So we need to calculate the input resistance and output resistance at the points given on the circuit. Our input looking directly at the source and our output looking directly at the drain. First thing is, we'll directly go to the AC model or the AC analysis. Assume that the DC is done, okay, and we'll go directly to the AC analysis. So let's simplify the circuit. In the AC analysis, all the capacitors will be short circuit. So this capacitor, C1, will be short circuit. This capacitor will be also short circuit. This capacitor, C2, will be short circuit. And then we deactivate the DC sources. So this DC source will be deactivated by making it ground. So now the circuit starts to look easier. And then you notice that R2 is connected between the gate and the ground. R1 is connected between the gate and the ground. So why don't we just plot R1 and R2 parallel to each other? So we can take R2, which is between the gate and the ground, we can plot it down. So we can plot R2 down here between the gate and the ground. And then notice that R1 and R2, they have a short circuit parallel to them. If R1 and R2, they have a short circuit parallel to them, this means that these two resistors are short circuited. You can't remove them, right? Because any current, it will go through the short circuit, and these two resistors will not get any current or any voltage across them. The voltage across them will be 0 because they are parallel with the short circuit, so you can just remove these two resistors and make the circuit much easier. Now let's plot the circuit starting from the input. As the usual procedure that we follow, always start with V input. So you can start by plotting V input here. After V input comes a resistance R input. This is what you should do when you solve these kind of problems. Start from V input, go step by step. Put your hand here and your hand here. So we have V input, R input. After R input, you have R4 to the ground. And then here, the source of the transistor comes. So the source of the transistor comes. So let's for now plot it like this. This is the transistor, the source comes. The gate of the transistor is connected to ground. And the drain of the transistor is connected by R3 to the ground and R7 to the ground. R3 to the ground, R7 to the ground. And this is V out. And then this is a middle like step. Let's now replace the transistor with the model. Which model you think we should use? As you see here, the gate is connected towards the ground. So it might be more convenient if we use the T model. Why? Because the T model, the gate will be connected to the middle point between the drain and the source. And if the middle point is connected to the ground, this means that we can separate the circuit into two parts, like this. So if we replace the T model, we can have here a dependent source, GM, VGS, and then we have here a link. This link will connect this point to ground, okay? And then here you have a resistance 1 over Gm. This is the source, don't forget this is the gate, and this is the drain. Why is it easier to use the T model? Because now you connected this point to ground in the middle, right? Which means that you can separate this circuit into two parts. One part connected to the ground here and one part connected to ground here, right? And once you separate the circuit into two parts, it will be easier to analyze, right? So we separated now the circuit into two parts, and this is the gate. VGS, by the way, VGS is the voltage VG minus VS. Here it's more convenient to deal, instead of VGS, we deal with VSG, because VSG is the voltage between the source and the gate. This is VSG, positive here and negative here. Because the gate is connected to the ground, right? So it's the VSG will be the voltage in this direction. But this dependent source is GM VGS. What we can do to make it easy, you can reverse this source and you call it GM VSG. So it's GM VGS in this direction or GM VSG in the other direction. So what we can do, we can put the source in this direction and we replace its value. Instead of VGS, we write VSG. So now we replaced everything in terms of VSG, because VSG is the positive voltage here. It's easier. Okay, so this is just a small trick, okay, to deal with a positive voltage. So instead of having VGS and the positive will be towards the ground and the current will be in this direction, we deal with VSG where the positive will be at the source and here the current, the dependent current source, we are going to reverse its direction and we call it VSG instead of VGS. Now, let's calculate the gain. First, we need the gain between V out and Vs. So we need the terminal gain between V out and Vs. V out equals what? V out equals this current multiplied by these two parallel resistors, right? Because you have a current here, it will go through these two resistors. So V out will be GM VSG multiplied by R3 parallel with R7, right? Over Vs. What is Vs? Vs is the same as VSG, right? Because the G is connected to the ground, the gate is connected to the ground. So Vs is the same as VSG. So VSG will cancel with VSG and you get the gain, the terminal gain, GM multiplied by R3 parallel with R7. This is the terminal gain. Next, we need to calculate the overall gain, the gain between V out and V in. You have to use whatever you calculated here. We already calculated V out over Vs. So we can say now that the overall gain, which is V out over V input, is V out over Vs multiplied by Vs over V input. We already calculated this, right? We already calculated this V out over Vs. So remaining, we need to calculate Vs over V input. Vs over V input is the voltage here across these two resistors. The voltage across these two resistors. This is Vs over V input. How do we calculate it? Very simple, voltage divider. Vs, the voltage here across divided by V input, is whatever resistance here divided over the sum. Don't say it's R4 over R1 plus R4. No. When you do a voltage divider, you take all the resistance here, all the resistance here. All the resistance here is R4 parallel with 1 over Gm, parallel with 1 over Gm. So here, this will be voltage divider between whatever here and R1. Whatever here is what? This parallel with this, R4 parallel with 1 over Gm divided over the sum, which is R1 plus R4 parallel with 1 over Gm. So when you do a voltage divider again, when you do a voltage divider between or in a circuit that looks like this, and you want to calculate Vs, then Vs over V input, don't say only this resistor over the sum. No, it's whatever you have here, the equivalent resistance that you have here over the sum. So the equivalent resistance that you have here is 1 over Gm parallel to R4. So you multiply this times this, you get the overall voltage gain, which will be Gm R3 parallel with R7 multiplied by this expression, which is R4 parallel with 1 over Gm over R1 plus R4 parallel with 1 over Gm. This is how we should do it. This is how we should do it. We should divide the gain into two parts. Relation between V out and Vs, and then a relation between Vs and V input, and you multiply them together. Next, we are asked to calculate R input looking directly at the source. Looking directly at the source, which means that we need, this is the source. You need to ignore everything before. This is the source. We need to calculate R input looking directly at the source. So basically, if you look directly at the source, the only resistance that you will see is what? 1 over Gm. So R input will be equal to 1 over Gm, right? And then let's go back to the original circuit. Let's go back to the original circuit. We had a resistance here R4, a resistance here Ri. Sorry, this is Ri, not R1. This is Ri. Okay. We have a resistance here Ri and then a source Vi. We need to calculate R output looking directly at the drain. R output looking directly at the drain. So here, this is the drain. Okay. The drain is here and the drain was connected to other resistors. So we need to calculate R output looking from here. R output looking from here. Before all the resistors connected to the drain, we need to look at our output directly at the drain without all the resistors connected to the drain. So we just remove everything before this point. We remove everything before this point, and then, I'm sorry, maybe it's a bit confusing here. I have many things. Let me clean it a little bit. So we have here a resistance 1 over Gm. This is now our source. This is the ground, is the gate, and this is our circuit. And we need to look for our output from this point. So we removed everything before. Now we deactivate the independent sources. If we deactivate this, it will be a short circuit. Short circuit. Now, look at this part of the circuit. We have 3 resistors connected parallel together. Is there any current? Is there any current in these 3 resistors connected together without any source, without anything with them? Of course not. So 3 resistors, just 3 resistors connected in parallel without any source, the current will be 0. So 0 current here. And if you have a 0 current in this part. If you have a 0 current in this part, VSG will be what? VSG will be also 0. Because there is no current, so the drop between the source and the gate is 0. And if VSG is 0, this current source will be also 0. Current source 0 means what? Means open circuit, right? Means open circuit. So you can replace the current source here, the dependent current source, by an open circuit. You can replace it by an open circuit. So now when you look at R output from this point, you will see what? You will see open circuit. So R output will be infinity. Again, look at the sequence. We deactivated the independent source. We found that the current here is 0, and hence the voltage VSG is 0. So the dependent source will be 0, which means open circuit. So the resistance that you will see at this point will be infinity. Okay? So that's it for this example about the common gate amplifier. We'll see you in another example in the next video.